In past videos, we have learned how the CPU works, how to read assembler, and how to reverse engineer the functionality of a simple program. In the upcoming videos, I want to go a little bit deeper and explore how we can exploit a program when we have the ability to corrupt memory. The first video will be more about how to set up and get everything running, so we can focus on the technical part in the next videos. The title of this video is inspired by the famous Frack article Smashing the Stack for Fun and Profit from 1996. You can imagine that a lot of stuff has changed since then, though we first have to learn about the basics before we can have a look at modern techniques. We will kind of follow the timeline of exploitation techniques, discovery and attempted mitigations like DEP or ASLR, just to name two. As basis for the next couple of videos, I will use challenges included in the Linux images provided by exploitexercise.com. This allows you to set up the system as well, which I highly recommend. With Protostar, you will start with simple memory corruption and modification, function redirection, and finally executing custom shellcode. In order to make this as easy as possible to introduce, ASLR and non-executable memory has been disabled. So first download the Protostar ISO and boot from it in the VMware player. As you can see, it doesn't start with a nice graphical user interface like our Ubuntu system does. But don't panic, you learned how to use the command line from the very first episode. Now I will use this moment to introduce you to SSH, which stands for Secure Shell, and is a program that allows you to connect to a system over a network that has an SSH server running. This would be the kind of access you get when you have to administrate servers that run, for example, a website. That's the reason why I introduced you to the command line in the very first episode, because you really have to know how to use it. You can also tell that I run Windows as a host OS. I think I haven't mentioned it before, but the main reason here is that I imagine the majority of people start out on Windows, which means it's the best way to reach more people. We don't want to be excluding like so many other parts of our society. At least for me, hacking conveys a spirit to be open and share knowledge. So that's why I have to download PuTTY for Windows now, which is a Windows client for SSH. To use it to connect to this machine, we have to find the IP address of it. The username and password for the Protostar image is just user, so use that to log in. And then execute the command IP addr to find the assigned IP and then copy it into PuTTY, save the session and press open. You have to log in again, but this is much better now. We can copy data back and forth and we can have multiple connections. The equivalent for Mac and Linux is just simply type SSH, the username user at the IP address. Okay, at the moment our shell is bin sh. And as you can see, tab completion doesn't work. But we can execute bin bash instead, which makes the command line a bit nicer. So what do we have here? With uname-i we can see that system information, and we can see that we have a 32-bit Linux with a 2.6 kernel. So how does this work now? On the website it says the levels to be exploited can be found in the opt protostar bin directory. So let's have a look. ls to list all files in this directory. Immediately you will notice this weird red background color for the file names. Let's have a closer look. With files we can check the file type and it tells us that it's a setuid elf 32-bit executable. From earlier videos you may remember that we have never encountered setuid before. As always, if we want to know something in Linux, we can look into the Linux manual. Though the main page of setuid is actually about the setuid function provided by libc, but that doesn't bother us, because it might be related. So let's see what it says about this function. Setuid stands for set user identity, and setuid sets the effective user ID of the calling process. With cat passwd, we can see all users on the system. Remember, our user is called user, so we have the ID 1001. And root user has ID 0. So does that mean that we can simply write a C program as our unprivileged user and execute setuid with ID 0 to become root? Obviously not, that would be horrible. Further down it tells us about possible errors like eperm, which says that the user is not privileged and the UID does not match the real UID of the calling process. Okay, then what can it be used for? An example usage is that a root process might want to drop privileges to an unprivileged user, that in case the process gets exploited, the attacker does not gain root privileges. So if you have a process that has to start as root, but then doesn't need it anymore, it's good to drop them. Anyway, what does this have to do with our setuid binary? Let's open a second SSH session to look at all running processes. Now open a process that keeps running, something like a Vim editor. And then we can use the other shell to execute psaux to list all running processes. Now we have to search a bit, but here it is. The first column tells us the user of the running process, and because we as user have executed Vim, it will run with our privileges. So now let's execute one of those setuid binaries and do the same. Let's search the program name. Here it is. But do you see the first line? It says it's running as root. What the fuck? How is that possible? Let's have a look again at the file permissions. Okay, first of all, r-x means that anybody on the system can read this file and execute it. The next three permissions are the same and refer to the permissions of the group. A group is just an ID that multiple users could share. So we are in the group that is also called user. But theoretically, you could have multiple users together. Okay, now it gets interesting. The first character indicates if a file is a directory. Well, it's not. So the remaining three permissions are the owner of the file. The owner of the file is root. And the owner has the permission to read, write, and S? So the S replaced what should be X for executable. This is called the setuid bit. We have already looked at the running process, so you can guess what this does. When this bit is set and I as a regular user execute it, Linux will actually execute it with the privileges of the owner. So in this case it will run as root. Why the hell would somebody do this? There are two good examples. First, you may know sudo, which is a program that allows you to run something as root if you are a normal user. So how can sudo execute a program as root, even though you typed in the command? Well, it also has the setuid bit. Another great example is the ping program. Ping will also run as root because it has the setuid bit set. Why, you ask? Because ping wants to send an ICMP packet, which is a fairly low layer, and Linux generally doesn't allow normal users to create such raw packets. But because ping is not evil, somebody created a setuid binary to allow normal users to send ICMP packets. What if there is an exploit for a program like ping? That would allow you to execute arbitrary code as root, right? So it's clear that setuid can be really dangerous. Well, and that's the whole point of the challenge from Protostar. If we can exploit one of these programs here, we can escalate privileges and gain root. This is basically like jailbreaking on iPhones or rooting on Android devices. You try to find a vulnerability that allows you to execute arbitrary code in a privileged mode. Well, on those real devices, especially iOS, this is extremely fucking complicated, and a lot more layers are involved, but now you get a better imagination of the whole thing. One last thing before we start with the challenges, you know that you can debug programs, right? For example, you can use strace to spy on system calls, or simply use GDB, and GDB allows you to modify memory. So you could just open the setuid binary in GDB, modify the code, and execute whatever you want as root. Let's try it. Okay, it seems to run, so let's rerun it and look at the process list. As you can see, it doesn't run as root anymore. The reason is that GDB could not debug a process that runs as another user. So GDB actually forces the binary to not run as root, so it can actually debug it. So good idea, but unfortunately, or maybe fortunately, it's not that simple. I guess we have to rely on good old exploitation techniques. See you in the next video when we start with the first challenge.